EES, which is pronounced ease, is an acronym for Engineering Equation Solver. The last video in this section introduced the use of psychrometric property functions in ease. In this video, we'll use these property functions to solve a simple example problem, which is shown here. So this is an air conditioning system. A hot, humid air is drawn into the system with a volumetric flow rate of 100 CFM. The temperature of this hot outdoor air is 95 degrees Fahrenheit, and it has a relative humidity of 70%. In order to provide a comfortable environment, the air must be both cooled and dehumidified, and therefore the air first passes over a chilled water coil in order to cool it and dehumidify it. The air exits the chilled water coil at a temperature of 45 degrees Fahrenheit, and then it passes over a steam coil in order to reheat it to a more comfortable temperature, and the air then exits the steam coil at state 3 here, which is 65 degrees Fahrenheit. So we'll solve this problem using ease, and it'll be made a lot easier by using the psychrometric property functions, which use the air H2O fluid. So here we're going to enter the inputs in ease, and we'll start by determining the properties of the air entering the chilled water coil. So state 1 here, we need 3 properties to fix state 1 since we're dealing with the mixture, and the 3 properties are pressure, temperature, and relative humidity. And the properties that we'll get at state 1 include the humidity ratio with the function humrat, the dry air specific volume with the function volume, and the dry air specific enthalpy with the function enthalpy. So now we can calculate the mass flow rate of dry air entering the chilled water coil. We'll do that using the specified volumetric flow rate and the dry air specific volume. And then we can determine the temperature at which condensation will begin as the air flows through the chilled water coil, and we'll get that using the dew point function in ease. And solving here shows that the dew point of this air-water mixture is 83.7 degrees Fahrenheit, and that's of course higher than the exit temperature of the air-water mixture, and therefore we know that saturated air is going to be leaving the coil, and it will have then a relative humidity of 100%. So the state of the air leaving the chilled water coil is specified again by 3 properties, in this case pressure, temperature, and now the relative humidity has to be 1. So the humidity ratio and the dry air specific enthalpy here at state 2 can be obtained using the ease functions humrat and enthalpy. The mass flow rate of condensate that is forming in the chilled water coil can be obtained by carrying out a water mass balance on the chilled water coil. So that's shown here. We have the condensate is equal to the mass flow rate of dry air times the change in the humidity ratio. In the state of the pure water condensate that's leaving the chilled water coil is fixed by its pressure and temperature. We only need 2 properties because it's a pure substance, and so we can get the specific volume of the condensate and use that to compute the volumetric flow rate of condensate, which I've done here. And solving now leads to 0.93 gallons per hour of condensate leaving the chilled water coil. So the state of the air leaving the steam coil, that's finally provided to the conditioned space, which is state 3. It must be fixed again by 3 properties. In this case, it's fixed by the pressure, the temperature, and the humidity ratio, which will not change in the steam coil because water is not being added or removed. So here we're going to get the relative humidity and the dry air specific enthalpy at state 3 using the ease functions relhum and enthalpy. And if we solve here, we'll see that air is being provided to the conditioned space at a comfortable temperature and also a comfortable relative humidity of 48.2%. So finally, we can determine the rate of heat transfer to the chilled water in the chilled water coil using an energy balance on the coil, and that's shown here. You'll note that we're neglecting the small enthalpy term associated with the condensate. And we can also get the rate of heat transfer from the steam in the steam coil using an energy balance on the steam coil, which is shown here. So this is one of a series of tutorials meant to describe the operation of the ease software. If you'd like to get more information about ease, obtain the software, or access more of these tutorials, please go to the website fchart.com. These tutorials are excerpted from the book Mastering Ease, which can also be obtained from the fchart website.